This is an introduction to exponential functions, and exponential functions are a very important part of math, as there are lots of examples in the real world of exponential functions. Population growth, compound interest, there's lots of things out there, and so knowing this type of topic is going to be important. So let's look. We're going to start with an example. After graduation from college, you're probably going to be looking for a job. And let's assume you're going to be offered a job starting at $40,000 a year. And the company you work for is going to promise you a 4% raise every year. And let's figure out your salary for the first couple of years. So we have T is going to represent the number of years from your start date. And then at time 0, your salary is going to be the $40,000. So you work the first year, making $40,000. At the end of the first year, we're going to make that T equals 1. They give you that 4% raise. So to calculate that, you just take the 40,000, and if I want to calculate just the raise part of it, you're going to multiply by 0.04, and so you get a $1,600 raise, making your new salary $41,600. So the next year, when you get a raise, you're going to earn 4% on the $41,600 instead of the $40,000. So your raise is going to be slightly higher than the $1,600, and that's the beauty of compound interest. So at the end of year 2, I'm now going to calculate my raise based on the $41,600 times 0.04. So instead of $1,600, it's now $1,664, a little bit better. My new salary is what I get when I add the $1,664 to the $41,600, and I get $43,264. So if I fill out a table, I'm going to place some data in here. I have time 0, year 0, and my raise and my salary. So I'm going to fill this in. Remember, we started with 40,000. Then the raises kicked in. The first raise was $1,600, and my new salary was $41,600. And then the next raise was $1,664, because you're earning interest. You're earning a raise on your previous raise. So this is $43,264. The next time I get a raise, I'm going to make $1,730.56. So now my new salary is $44,994.56. And then finally, after 4 years, I'm almost getting an $1,800 raise. I'm just a few cents short of $1,800. So my final salary at year 4, at the end of year 4, is $46,794.34. So this is the beauty of compound interest and raises that are based on a percentage of pay. At year 0, I was making $40,000. At the end of year 1, 2, 3, at the end of year 4, so in 5 years, my salary has jumped up to almost $47,000. So a 4% raise year after year is pretty darn good. You might not see that out there unless you work for an energy company or something, or finance or something. Then you might see a lot more than that. But if I were to sketch this, I start at $40K, and at the end of year 1, 2, 3, 4, so this is time, this is money. And if I was going to 40, 41, 42, 43, 44, and I'm almost going to be off the graph. So at the end of year 1, I was at about here. Here's my initial. End of year 2, I was 41, 42, 43 and some change. End of year 3, and I'm up at 45. And then end of year 4, and I'm up at 47. So it increases in a hurry, which is a nice thing if you're talking about money. The raise amount is not constant, so I'm not going up at a constant rate. My salary is not increasing linearly, but it can be modeled by an exponential function, which is usually better. So this is an exponential relationship. That's when it's increasing. We can also have a model where the value is decreasing, and a popular example is buying a new car. When you purchase a new car, as soon as you drive it off the parking lot, it's going to depreciate in value. You cannot sell it for what you bought it for. So let's say you bought a new car and you paid $24,000, and this particular car had a depreciation rate of 3% per year. So I'm going to decrease in value. If I want to calculate the amount of decrease after the first year, I take the 24,000, and to that I multiply by the 3%, 0.03, and that's going to be $720. That's how much I'm going to reduce the 24,000 by. So 24,000 minus 720 leaves me with 23,280. This is kind of, if you know what a Kelley Blue Book is or an Edmunds estimate, this is what they do. They calculate the depreciation of specific cars based on a lot of factors. We're kind of simplifying it here. So after year 2, you do this again, and you now are at 23,280, and you're going to subtract whatever depreciation is. I get that by taking 23,280 and multiply by 0.03. And now my car is only worth $22,581.60. So we're going to fill out this table of values. The car value at year, right when you buy it, is $24,000. After year 1, I have to knock down the price by $720, so $23,280. The depreciation the next year is $698.4. So I'm now down to $22,581.60. And then I'm down to I'm going to knock off another $677.45. And that's now down to $21,904. So if I were to roughly sketch this, I would start at 24,000. And this time, my car is going to depreciate kind of like that. It's going to decrease, and then eventually it's going to kind of level out, because it's never going to depreciate all the way down to 0. And each time you calculate it, because your original value is decreasing, the amount you're taking off is getting smaller as opposed to getting larger. So if you think of those two examples, the first example where you're calculating your raise, that demonstrates exponential growth. Everything is increasing. And that's good when we're talking about money. And then example 2 represents exponential decay. But whether it's growth or decay, we can represent both of those things with one formula. And this formula is going to be my y value as a function of time, a times b to the t. And we are assuming that my base is going to be a positive number. Otherwise, it's going to get wonky, and we're not going to do that in this class. So a is always going to be the initial amount. You need to get really familiar with this formula. We're going to use it all year. A is the initial value, which should make sense, because when time is 0, I don't care what b is. Any base raised to an exponent of 0 is going to be 1. So this part would be 1, and you're left with a. That's why a is the initial value. B we call the growth factor. That is not the rate. The rate is embedded in the growth factor, and b, to get b, it's going to be equal to 1 plus the rate. So r is the rate as a decimal. Okay. If I have exponential growth, then the rate is positive. If I have exponential decay, then the rate is negative. My growth factor is always going to be a positive number, though, because I'm not going to have a rate that's going to be make this negative. Okay, so my rate's always going to be a percent between 0 and 100 if it's going to be, especially if it's going to be decay. So well, let's take a look at some graphs. So if I have exponential growth, my graph is going to look a certain way, and if I have decay, it's going to look different. So my basic function is still y is equal to a times b to the t. For both graphs, I'm going to cross at my initial value a. Okay, it doesn't matter whether it's growth or decay. But if I have exponential growth, then I cross at a, and my graph is going to increase. And exponential growth is denoted by a growth factor greater than 1. If it's 1, then you just get a flat line. Decay, again, crosses, the initial value crosses the y-axis, and he's going to decrease. So for decay, my growth factor is between 0 and 1. My growth factor is still positive, but it is less than 1. So we're going to work an example or two here, and then we'll cover a little bit more in class. So this is an example taken from the pre-calculus book that FLCC uses. So we'll look at this. Carbon-14 decays at a rate of 11.4% every 1,000 years. Decays. So when you see the word decay, that means this rate is going to be negative. So my percentage is my rate. My rate is going to be negative 0.114, because the rate is converted to a decimal every 1,000 years. We want to write a formula for the quantity of a 200 microgram sample remaining as a function of time in thousands of years. So this is thousands of years, this is thousands of years. We don't have to do anything to convert one to the other. They are consistent. So the quantity Q, when you look at this example, think about what this would represent. And when I think about my original formula, in this case, when I have a quantity Q, then I'm going to be fancy. Instead of y, I'm going to say Q is a function of t. That just means the quantity is a function of time. But everything else is the same. A times b, and time is my variable, t. So I can find b. B is going to be the rate added to 1. So it's 1 plus a negative 0.114. Okay, so my growth factor is less than 1, but it's still positive. It's 0.886. That means everything's decaying. Now I need an initial value. Well, I was given the initial value. It's 200 micrograms. So now all I have to do is substitute it in. And we are just looking for a formula. So it's 200 times 0.886, and t is my exponent. You have to be careful with these problems. You cannot multiply the 200 and the 0.886. If I'm going to evaluate this, if I want to find Q of 3, perhaps, then I would substitute the 3 in for the t. I would raise 0.886 to an exponent of 3, and then I would multiply the 200. But this is the function, and that's all you had to do was find the function. For the next example, I'd like you to pause the video and see if you can figure this out yourself. In 1980, the population of Mexico was 67.38 million, and it was growing at an annual rate of 2.6%. I just want a formula that represents the population of Mexico where T0 represents 1980. So pause the video, please, and you write the formula out, and we will check this one in class. As a final check, we have a sketch here of 3 different functions, and these are not in order over here. I have 3 different functions written out. I want you to look at the graph and match up the graph to the corresponding function. And again, we will go over that in class. So you can pause the video, sketch all this out, and see what you can do, and be ready to justify your answer in class.